So here's something you probably did today without thinking about it. You tapped a link, or you clicked one, and a page appeared. Maybe it took half a second, maybe a little longer if the connection was slow. But from where you were sitting, it looked like one thing happened. You asked, and the answer showed up. What's strange about that, and this is worth sitting with for a moment, is that the page was never inside the link. The link was just an address written on a scrap of paper. And when you clicked it, your device had to figure out what that address actually pointed to, where in the world to send the question, how to ask it in a language the other side would understand, and how to get the answer back to your screen in a form you could read. All of it in roughly half a second. Tonight we're going to follow one imaginary click on that entire journey, out from your device and back again. We'll trace every step the request takes, through systems most people never think about, across networks that were built over decades by people solving problems that didn't exist yet. And we'll do it slowly, because there's no rush. The systems we're going to walk through aren't going anywhere. They've been quietly running underneath every page you've ever loaded, every message you've ever sent, every video you've ever watched. They were running before you woke up this morning, and they'll still be running after you fall asleep tonight. Let's start with the moment right after the click, because what happens inside your device in the first few milliseconds deserves a closer look. When your finger lifts off the mouse button or the touchscreen, the operating system registers that a press and release occurred at a specific point on the display. It passes that event to whatever application owns that region of the screen, which in this case is your browser. The browser looks at the element under the cursor, identifies it as a link, and reads the address attached to it. All of that, the detection of the gesture, the identification of the element, the extraction of the address, happens inside your own machine before anything reaches the network. The journey begins not with a signal sent outward, but with your own device quietly reading a small piece of text. That piece of text is a URL, a uniform resource locator, and it has a very specific structure, even though it reads like a single, unbroken string. The first part is the scheme, which tells the browser what protocol to use. For most web pages, the scheme is either HTTP or HTTPS, with the S indicating that the connection should be encrypted. After the scheme comes the host, the name of the server the browser needs to contact. There may also be a port number, though most of the time the browser assumes a default based on the scheme and the port is left unwritten. After the host comes the path, which identifies a specific resource on that server, the way a file path identifies a document on your own computer. There can also be a query, a set of parameters that modify what the server returns, and a fragment, which points to a particular section within the document. The fragment is notable because the browser never sends it to the server. It keeps the fragment to itself and uses it locally, after the page arrives, to scroll to the right place. Before the browser contacts anyone, it checks whether it already has a usable answer sitting in its own storage. Browsers maintain a private cache of responses they have received from servers in the past. When the server originally sent each of those responses, it included instructions about whether and for how long the browser was allowed to reuse the stored copy. If the browser finds a cached representation of the resource you just requested, and if the server's caching rules say that copy is still fresh, the browser can serve it immediately. The page appears on your screen without a single byte leaving your device. The journey ends before it begins, answered entirely from local memory. This is one of the most effective performance features of the entire web, and it works because HTTP was designed from the start with caching as a first-class concept, not an afterthought. Even when the cached copy is no longer considered fresh, the browser can ask the server a lighter question: has this resource changed since the copy I already have? If the server says no, the browser reuses what it stored, saving the cost of transferring the full response again. But if no usable cached copy exists, the browser needs to reach out across the network and fetch the resource, and the very first thing it must do is figure out where to send the request. The URL gave it a host name, a human-readable label, and now the browser needs to translate that label into a network address that the routing infrastructure can actually work with. To understand why that translation is harder than it sounds, it helps to know a little about how addresses work on the internet. Every device connected to the internet has a number assigned to it. Think of it like a phone number for a machine. When your device wants to talk to another device, it needs to know that number. The number is called an IP address, and it's the actual identifier that the network uses to route information from one place to another. But you almost never type an IP address into your browser. What you type, or what a link contains, is a name, something like example.com, a name that a person can read and remember, but that the network itself can't do anything with. The network only speaks numbers. So there has to be a translation step. Something has to take the human-readable name and turn it into the machine-readable number. And that something is the domain name system, which people usually just call DNS. It's one of the oldest and most fundamental pieces of infrastructure on the internet, and it's working constantly, quietly, underneath almost everything you do online. Here's how it actually works, and the design is genuinely clever when you think about what it had to solve. In the early days of networked computing, back in the 1970s and into the early 1980s, there was no DNS. There was just a file, a single text file called the host table, maintained by a small group at the Stanford Research Institute, and every networked computer had a copy. The file listed every host name and its corresponding number. If you wanted to add a new machine to the network, someone updated the file, and everyone else downloaded the new version. That worked when the network had a few hundred machines. You could fit every name and number in a file that was a few kilobytes long, and updating it once or twice a week was manageable. But by the early 1980s, the network was growing too fast. Every time a new machine came online, the file needed updating. Every machine on the network needed to download the new version. The file was getting too large, the updates were too frequent, and the whole approach had a single point of failure sitting right in the middle of it. If the people maintaining that file went on vacation, or if their server went down, the entire naming system stopped getting updated. So in 1983 and 84, a computer scientist named Paul Mockapetris designed DNS as a replacement. He published the design through the Internet Engineering Task Force in 2 documents that laid out the whole system. The key insight was distribution. Instead of one file that knows every name, DNS spreads the work across a vast hierarchy of servers, each one responsible for a different piece of the naming space. And it uses caching, which means that once a server has looked up an answer, it can remember that answer for a while and serve it again without asking the same question twice. Mockapetris's design divided the naming space into zones. Each zone is managed independently by whoever is responsible for that part of the namespace. The owner of a domain controls the records for that domain. The operators of the .com zone control the pointers that say which servers are authoritative for each .com domain. And at the very top of the hierarchy sit the root servers, which know where to find the servers for every top-level zone. The design also specified something called time to live, which is how long a cached answer should be considered valid. When a server sends you an answer, it includes a time to live value that says, you can trust this for the next 300 seconds, or this is good for a day. After that time expires, the cached answer is discarded, and the next query for that name has to go through the hierarchy again. This means that when someone changes the records for a domain, the change propagates through the system naturally as old cached answers expire and fresh queries pull the new information. The system Mockapetris designed in those documents is essentially the same system running tonight, more than 40 years later, handling billions of lookups every day across the entire internet. So when your device needs to translate a name into a number, here's what happens step by step. Your device first checks its own memory. Operating systems keep a small local cache of recent DNS lookups. If you visited the same site 5 minutes ago, the answer might still be sitting right there on your machine, and the lookup is finished before it even touches the network. If the answer isn't cached locally, your device sends the question to a server called a recursive resolver. This is usually a server run by your internet service provider, or it might be a public resolver run by a company like Google or Cloudflare. You probably didn't choose this server consciously. Your router handed it to your device automatically when you connected to the network. But the recursive resolver is the one that does the actual legwork of tracking down the answer, and it does it by following the hierarchy. Think of it like asking for directions in a city you've never visited. You don't go straight to the address. You ask someone at the airport, and they tell you which part of the city to go to. You go to that part of the city and ask again, and someone there tells you which street. You go to the street and ask again, and someone there points you to the building. Each person you ask knows a little more about where you're going, and each one narrows it down until you arrive. DNS works the same way. The recursive resolver starts by asking a root server. At the top of the DNS hierarchy sit the root servers. There are 13 named root server identities, which are labeled with letters from A through M. But that number, 13, is a little misleading, because each of those 13 identities is actually served by many individual server instances spread around the world. The organization that coordinates the root system, ICANN, reports that there are now more than 1,500 individual root server instances globally. So when people say 13 root servers, what they really mean is 13 addresses that are answered by hundreds or thousands of machines through a technique called anycast, where the same address is advertised from many different physical locations, and the network automatically routes each query to whichever instance is closest. The root servers don't know the final answer to your query. They don't know what number goes with example.com. What they know is where to find the servers responsible for the .com zone. They hand back a referral, pointing the resolver toward the .com name servers. The resolver then asks the .com name servers the same question, and those servers don't know the final answer either. They know which servers are authoritative for the specific domain, example.com, and they hand back another referral. Finally, the resolver asks the authoritative servers for example.com, and those servers have the actual answer. They know what IP address goes with that name. The resolver collects the answer, caches it for the duration specified by the time to live value, and sends it back to your device. The whole thing typically takes a few tens of milliseconds when nothing is cached. But in practice, many of these answers are already cached at various levels of the hierarchy. Your recursive resolver has probably answered questions about the .com zone thousands of times today, so it doesn't need to ask the root. It might have the answer for the specific domain cached from a query it handled minutes ago. The more popular a domain is, the more likely the answer is already sitting in a cache nearby, and the faster the lookup completes. For very popular sites, the DNS step might take barely a millisecond. And here's something that stands out about this design. It's not just clever engineering. It's a genuinely elegant solution to a coordination problem. Nobody owns DNS. No single organization controls the whole system. ICANN coordinates the root, but the actual root servers are operated by a mix of organizations, including universities, government agencies, military organizations, and private companies, spread across dozens of countries. Each domain owner controls their own authoritative servers. Each internet provider runs their own resolvers, and the whole thing holds together through a set of shared rules that everyone agrees to follow, not because anyone forces them to, but because the system only works if they do. The cooperative trust that DNS depends on is one of those things that sounds fragile, but has proven remarkably durable. People have been predicting the collapse of the DNS system for decades, and it keeps working, because everyone who depends on it has a mutual interest in keeping it working. It's cooperation enforced by shared necessity, not by any central authority. There is a distinction in DNS that explains how the labor is divided across the system, and it helps to see it clearly. When your device sends a query to the recursive resolver, it is asking for a complete answer. It says, "Here is a name, please come back with the address." The resolver accepts that responsibility and does all the walking, contacting root servers, following referrals, querying authoritative servers, and assembling the final result. This style is called recursive resolution, and it is the mode your device uses because your device does not want to manage the chain of referrals itself. But the conversations that the recursive resolver has with each server along the hierarchy use a different style. When the resolver contacts a root server, the root server does not go off and track down the complete answer on the resolver's behalf. It simply says, "I don't know the final answer, but here are the servers responsible for the next zone down. Try them." Each server in the chain does the same. It answers only what it directly knows and points the resolver onward. This style is called iterative resolution. The resolver does the traveling. The servers it visits along the way stand still and give directions. The entire lookup is a hybrid of the two styles, recursive from your device's perspective and iterative from the resolver's perspective as it steps through the hierarchy. The answers that come back from authoritative servers are not always simple address records. DNS stores several types of resource records, each serving a different purpose. An address record maps a name directly to the IP number your device needs. But sometimes the authoritative server returns a different kind of record, one that says, "This name is actually an alias for another name," and the resolver must follow the alias and resolve the new name in turn. There are also records that identify which servers handle email for a domain, records that publish cryptographic keys used to verify the authenticity of other DNS data, and records that hold plain descriptive text. The resolver follows whatever chain of records it encounters until it arrives at a definitive answer. And sometimes the definitive answer is that there is no answer at all. If you request a name that genuinely does not exist within a zone, the authoritative server for that zone will say so explicitly. This negative response can also be cached for a duration governed by a value set by the zone's administrator, so that neither the resolver nor any server further up the chain wastes effort answering the same impossible question again. The ability to cache a confirmed absence is a small but important feature of the original design. Without it, every mistyped address would generate a fresh cascade of queries through the hierarchy each time someone requested it. Now your device has a number. It knows where to send the request, but knowing where to send something and actually getting it there are two very different problems, and this is where the data steps off your device and onto the local network for the first time. When your device constructs a packet to send across the internet, it wraps the data in layers, each one serving a different audience. The innermost layer holds the content of your request. Around that sits a transport header that identifies which conversation this data belongs to. Around that sits the IP header, carrying the source address and the destination address, the two numbers that the global routing infrastructure will use to move the packet from your device to the server. But the IP layer alone cannot place the packet onto a physical wire or a radio channel. For that, your device adds one more envelope, called a frame, and the frame is addressed not to the distant server, but to the next device on the local network that can carry the packet forward. On most networks, that next device is a gateway, a router that sits at the boundary between your local network and the broader infrastructure of your internet service provider. Your device knows the gateway's local address because the network told it automatically during setup. At the same moment, it learned which DNS resolver to use. So the frame your device constructs carries the gateway's local address as its destination, even though the IP header inside still points to a server that might be on the other side of the world. The frame says, "Deliver this to the gateway right here on this network." The IP header says, "This packet ultimately belongs somewhere far away." When the gateway receives the frame, it peels off the local envelope and reads the IP header inside. It makes a routing decision about where to forward the packet next, wraps the packet in a fresh frame addressed to the next device along the path, and sends it onward. At that next device, the same thing happens again. The frame is removed, the IP header is read, a new frame is built, and the packet moves one hop closer to its destination. At every hop along the chain, the frame envelope changes. The local addresses stamped on the frame are rewritten to suit whatever link the packet is crossing at that moment, but the IP header, carrying the source and destination addresses of the original exchange, passes through every hop untouched. The outer wrapping is temporary and local. The inner addressing is global and persistent. This is the quiet distinction between a destination and a route. The IP header states where the packet wants to arrive. The forwarding decisions at each hop determine how it gets there. The packet itself carries no map and stores no memory of the hops it has already crossed. It simply declares a destination and trusts each device along the way to make a reasonable next step. The entire journey from your device to the server is built from a long chain of these small, local, independent forwarding decisions, each one nudging the packet a little closer to a place it has never been. And this is where we step into the part of the journey that most people never think about, because it involves the physical and logical infrastructure that carries your data from one place to another. Your request needs to travel from your device to the server that has the page you asked for. Depending on where that server is, your request might travel across a room, across a city, across a country, or across an ocean. And it does this not as a single unbroken message, but as a series of small pieces called packets. The idea of breaking a message into packets and sending them independently, then reassembling them at the other end, is one of the foundational ideas of computer networking, and it has a history that's worth knowing, because the idea was genuinely new when it was first proposed, and it came from people who were thinking about different problems in different countries and arrived at the same solution independently. In Britain in the early 1960s, a physicist and computer scientist named Donald Davies was working at the National Physical Laboratory, the same institution that had been home to Alan Turing years earlier. Davies was thinking about how to build a communication network for computers, and he realized that the traditional approach, the way the telephone system worked, wasn't going to scale. The telephone system used something called circuit switching. When you made a phone call, the network established a dedicated physical connection between you and the person you were calling. That connection was reserved for you for the entire duration of the call, whether you were talking or sitting in silence. It was simple, but it was wasteful. Most of the time on a phone call, nobody is speaking. The circuit sits idle, but nobody else can use it. Davies proposed something different. Instead of reserving a connection, you would break your message into small pieces, what he called packets, and send each one independently through the network. Each packet would carry its own address, and the network would route each one toward its destination, potentially along different paths. At the other end, the packets would be reassembled into the original message. The network's capacity would be shared among everyone using it, moment by moment, with no wasted reservations. Davies coined the word packet for these pieces of data, and his team at the NPL built a small packet-switched network to prove the concept worked. Around the same time, in the United States, a researcher named Paul Baran at the Rand Corporation was thinking about the same problem from a completely different angle. Baran was concerned about the vulnerability of communication networks to attack. The Cold War was at its height, and military planners worried that a nuclear strike could knock out centralized communication systems. Baran proposed a distributed network with no central hub, where messages would be broken into pieces, and each piece would find its own way through a mesh of connections. If part of the network was destroyed, the remaining nodes could route around the damage. And Leonard Kleinrock at UCLA was working on the mathematical theory of data flow through networks, developing queuing theory that would help predict how packets would behave as they moved through shared network resources. These ideas came together in a project funded by the Defense Advanced Research Projects Agency, usually called DARPA. In 1969, DARPA connected 4 nodes into a network called UCLA, the Stanford Research Institute, UC Santa Barbara, and the University of Utah. The early transmissions between those nodes proved that the concept worked. Messages could be broken into packets, sent across a network, and reassembled correctly at the destination. Over the next decade and a half, the network grew from 4 nodes to hundreds, and the protocols that governed how data moved evolved through several generations. In 1983, ARPANET switched to a new set of protocols that would become the foundation of the modern Internet. That switch, from the older protocol to TCP and IP, is often described as the moment the Internet was born, though like most births in technology, it was less a single moment and more a gradual transition. The Internet Protocol, IP, handles the actual delivery of individual packets. Its job is addressing and routing. Every packet gets a header that includes the source address and the destination address, and the network uses that information to move the packet toward its destination, one hop at a time, through a chain of devices called routers. Here's something important about how this works, and it seems obvious once you hear it, but people rarely think about it. When your device sends a packet, it doesn't plan the entire route in advance. Your computer doesn't have a map of the Internet. It doesn't know which routers are between you and the destination. It doesn't need to. All it does is hand the packet to the nearest router, which is usually inside your home network or at your Internet service provider. That first router looks at the destination address on the packet, consults a table of routing information that it maintains, and makes a decision about where to forward it next. It picks the next hop, the next router in the chain that seems like a good step toward the destination, and it sends the packet there. That next router does exactly the same thing. It looks at the destination, checks its own routing table, and forwards the packet to the next hop, and this continues, router by router, each one making an independent local decision based on its current understanding of the network's topology. No single router knows the entire path. Each one only needs to know the best next step from where it is. The routing information that each router uses comes from a protocol called the Border Gateway Protocol, or BGP, and understanding BGP, even at a high level, helps explain something fundamental about how the Internet actually works. The Internet is actually thousands of separate networks joined together, and each individual network is called an autonomous system. Your Internet service provider is one autonomous system. A large technology company might run several. Universities, governments, hosting providers, content delivery networks. Each one runs its own autonomous system. There are tens of thousands of them worldwide, and they connect to each other through various arrangements, some commercial, some cooperative, some mandated by regulation. BGP is the protocol these autonomous systems use to share routing information with each other. Each system uses BGP to advertise the addresses it can serve and the paths available through it to reach other parts of the Internet. When your Internet provider receives these advertisements from its neighbors, it builds a picture of which addresses can be reached through which paths, and it uses that picture to populate the routing tables that its routers consult when forwarding your packets. The route your data takes through the Internet isn't necessarily the shortest physical path between you and the destination. BGP doesn't optimize for geographic distance. It optimizes for reachability and policy. The path is shaped by which networks have agreements with each other, who has paid whom for transit, where traffic is allowed to flow, and which paths have been filtered out by policy decisions. A packet traveling from London to Paris might route through Frankfurt, not because Frankfurt is on the way, but because the networks involved have agreed to exchange traffic at an Internet exchange point there. And the routes can change at any time. If a cable is cut, or a router fails, or a network changes its peering arrangements, the BGP advertisements update, the routing tables adjust, and packets find a new path. This happens constantly, thousands of times a day across the global Internet. It's part of what makes the Internet resilient. There's usually no single route that everything depends on. The network is built to route around damage, to find alternative paths when the usual ones aren't available. This routing process, from your device through a chain of routers across multiple autonomous systems, usually takes just a few milliseconds within a continent. A packet traveling from one side of the United States to the other passes through a chain of routers and typically arrives within tens of milliseconds. A packet crossing an ocean adds more, depending on the distance. We'll get to the physical reality of those ocean crossings shortly. Now, while all of this routing is happening at the network level, there's another layer of work happening simultaneously that's just as important, because the Internet Protocol handles delivery of individual packets, but it makes no promises about that delivery. IP is what engineers call a best effort service. It tries to deliver your packets, but packets can be lost. They can arrive out of order. They can be duplicated. They can be delayed. IP doesn't care. Its job is to make a reasonable effort to get each packet from source to destination, and if it fails, it shrugs and moves on. This separation is not an accident or a compromise. It is a deliberate design choice, and the reasoning behind it matters. The designers of the Internet Protocol suite could have built reliability into IP itself. They could have made every router along the path responsible for detecting lost packets and requesting retransmissions, but that would have made the network layer far more complex, far slower, and far less flexible. Some applications need every byte delivered in perfect order. A web page with a missing paragraph is broken, but other applications can tolerate loss gracefully. A live video call works fine if a frame is dropped now and then, because by the time a retransmitted frame arrived, it would already be too stale to display. A sensor sending temperature readings every second does not care if one reading vanishes, because the next is already on its way. By keeping the network layer simple and best effort, the designers left the decision about reliability to the endpoints themselves. Applications that need guarantees use a transport protocol that provides them. Applications that prefer speed over perfection use a lighter transport that stays out of the way. The network carries packets without opinions about what those packets contain or how much any particular one matters. This is the principle that allows a single network to carry everything from surgery over a video link to a weather station reporting once a minute, each application choosing exactly the level of assurance it requires. For loading a web page, you need more than best effort. You need certainty. You need to know that every piece of the page arrived, that nothing was lost or scrambled, and that the pieces are in the right order. And that's the job of the transport layer, the set of protocols that sit on top of IP and provide the reliability guarantees that applications need. The transport protocol most people have heard of is TCP, the Transmission Control Protocol. TCP has been around since the 1970s, and it remains a load-bearing piece of the entire Internet stack. TCP works by establishing what's called a connection between your device and the server. Before any data is exchanged, the two sides go through a process, sometimes called a three-way handshake. Your device sends a message to the server saying, "I'd like to start a connection, and here's my initial sequence number." The server responds with its own sequence number and an acknowledgement of yours. Your device acknowledges the server's number, and the connection is open. This takes one round trip. Your device sends a message, the server replies, and now both sides are synchronized. Once the connection is established, data flows in both directions as a stream of bytes. TCP divides this stream into segments, each one numbered sequentially, and hands them to IP for delivery. As the server receives these segments, it sends acknowledgements back to your device confirming what it received. If your device doesn't get an acknowledgement within a certain time, it assumes the segment was lost and sends it again. If segments arrive out of order, TCP sorts them back into the correct sequence before handing the data up to the browser. The acknowledgement system deserves a closer look because it is the heartbeat that keeps the connection honest. When the server receives segments, it sends back a cumulative acknowledgement, a message that effectively says, "I have received everything up through this point in the stream." If the server has received segments 1 through 40, but is still waiting for segment 41, it keeps acknowledging through 40, even as later segments arrive and sit in its buffer. Your device notices that the acknowledgements have stalled at the same point and interprets the pattern of repeated acknowledgements as evidence that something was lost near that boundary. It retransmits the missing data without waiting to be asked, because the stalled acknowledgements are signal enough. This is the mechanism that turns an unreliable network into a reliable channel. Every byte that enters the stream at one end is tracked, confirmed, and if necessary, resent until it arrives at the other end. The cost is overhead. Every acknowledgement is itself a packet traveling back across the network, and every retransmission uses bandwidth that could carry new data. But the trade-off is worthwhile for applications that cannot tolerate gaps, and web browsing is one of them. TCP also manages something called flow control and congestion control. Flow control prevents a fast sender from overwhelming a slow receiver by letting the receiver tell the sender how much data it's ready to accept at any given time. Congestion control is trickier. It's how TCP tries to avoid overloading the network itself. TCP starts by sending data slowly, increases its speed as acknowledgements come back, confirming that data is getting through, and backs off sharply if it detects signs of congestion, like lost packets. Over time, TCP finds a sending rate that uses the available bandwidth efficiently without causing too much congestion. It's a continuous negotiation between being fast enough to be useful and cautious enough not to make things worse for everyone else on the network. What makes congestion control quietly remarkable is that it solves a problem no single sender can observe directly. Your device cannot see the state of every link between itself and the server. It cannot know which routers are busy and which are idle. So TCP infers congestion from the only signal available to it, which is the pattern of acknowledgements and losses. When packets are acknowledged promptly, conditions are probably favorable, and TCP gradually increases its sending rate. When packets go missing or acknowledgements arrive with unusual delays, something along the path is likely overwhelmed, and TCP reduces its rate to give the network room to recover. Every TCP connection on the internet is running this same quiet calculation independently, and the aggregate effect is that the network stays usable even when millions of senders share the same links. The result of all this machinery is that applications sitting on top of TCP see a simple, reliable, ordered stream of bytes. They can write data into the stream and trust that it will arrive at the other end, in order, without gaps, without corruption. TCP hides all the complexity of packet loss, reordering, retransmission, and congestion behind a clean abstraction. It's the protocol that provides the illusion of a direct pipe between two machines, even though underneath, the packets are bouncing independently through a chaotic network of routers. But TCP isn't the only option anymore for web traffic. In recent years, a newer transport protocol called QUIC has become widespread. QUIC was originally developed at Google, then standardized through the Internet Engineering Task Force, and published as a formal specification. It's now used by many of the largest websites and services on the Internet. QUIC takes a different approach from TCP. Instead of running directly on top of IP, QUIC runs on top of another protocol called UDP, the User Datagram Protocol. UDP is about as bare bones as a transport protocol can be. It adds port numbers to IP's addressing, which lets multiple applications on the same machine share the network, but otherwise it provides no reliability, no ordering, no connection management. It just sends individual datagrams and hopes for the best. QUIC builds reliability on top of UDP, including connection management, loss detection, retransmission, and congestion control. But it provides ordered delivery within each of its independent streams, rather than across one single byte stream. And that difference, along with others, is significant. The first major difference is encryption. QUIC has encryption built into the protocol from the ground up. With TCP, the transport connection and the encryption are separate concerns handled by separate protocols. You first establish a TCP connection, which takes one round trip. Then you establish an encrypted session using TLS on top of that connection, which typically takes another round trip. With QUIC, the transport handshake and the cryptographic handshake happen together, combined into a single exchange. On the first connection to a new server, this saves one round trip compared to TCP plus TLS. And on a return visit to a server you've connected to before, QUIC can sometimes resume the previous cryptographic state and begin sending encrypted data immediately, with no handshake round trips at all. The second major difference is how QUIC handles multiple streams of data within a single connection. With TCP, everything flowing over a connection shares a single ordered byte stream. If packet number 400 is lost, everything after it has to wait. Packets 401, 402, and all the rest sit in a buffer at the receiver until packet 400 is retransmitted and arrives. This is called head-of-line blocking, and it's a real problem when you're loading a web page that requires many different resources simultaneously. An image, a style sheet, and a script might all be flowing over the same TCP connection, and a lost packet in the image data blocks the style sheet and the script from being processed, even though they have nothing to do with each other. QUIC solves this by supporting multiple independent streams within a single connection. Each stream has its own ordering and its own loss recovery. If a packet belonging to the image stream is lost, only the image stream waits for the retransmission. The style sheet and the script, traveling on their own streams, keep flowing without interruption. This is a meaningful improvement for web performance, especially on connections with higher packet loss, like mobile networks. Whether your request travels over TCP or QUIC depends on the server you're connecting to and the browser you're using. Many large websites and services now support QUIC and the version of HTTP that runs on top of it, but plenty of others still use TCP with earlier versions of HTTP. Your browser negotiates which protocol to use during the connection process, and it happens automatically, without you needing to know or care which one was chosen. There is one more quality of QUIC that tends to get overlooked in a list of technical improvements, but it matters in daily life. QUIC connections can survive a change of network address. With TCP, a connection is identified by the combination of the source address, the source port, the destination address, and the destination port. If any of those values change, the connection is destroyed. This happens regularly in daily life. When your phone switches from a Wi-Fi network to a cellular network, its address changes, and every TCP connection it had open is silently broken. The browser has to establish fresh connections, repeat handshakes, and re-request anything that was in progress. QUIC avoids this by identifying each connection with its own identifier that is independent of the network addresses underneath. When your phone moves from Wi-Fi to cellular and its address changes, the QUIC connection can continue on the new address without a fresh handshake, because both sides recognize each other by the connection identifier rather than by the addresses on the packets. The transition can be nearly invisible to the application above. The version of HTTP designed to run on top of QUIC is called HTTP version 3. It carries the same requests and responses, the same methods, the same headers, the same status codes as earlier versions, but it benefits from everything QUIC provides: the combined transport and cryptographic handshake, the independent streams, the resilience to network changes. It is not yet universal. Many servers support it. Many others still serve traffic over TCP with earlier versions of HTTP, and your browser quietly negotiates which version to use as part of the connection process. Now, regardless of whether the transport layer is TCP or QUIC, there's one more critical step before your actual request can be sent. Your device and the server need to establish trust. They need to verify each other's identity and set up an encrypted channel so that the data flowing between them can't be read or tampered with by anyone sitting between the two endpoints. And this is where TLS comes in. TLS stands for Transport Layer Security. It's the protocol that puts the S in HTTPS. When you see that padlock icon in your browser's address bar, it means a TLS-protected connection is active between your browser and the server. The current version is TLS 1.3, standardized in 2018, and the handshake process it uses is a remarkable piece of applied cryptography. Here's what happens, in broad terms. Your device sends a message to the server, a client hello, that says, "I'd like to establish a secure connection, and here are the cryptographic methods I support, and a piece of random data I generated." The server picks one of the offered methods, generates its own random data, and sends back a server hello, along with its digital certificate. The certificate is a document signed by a trusted certificate authority. an organization whose public key is already known to your operating system or browser. The certificate binds the server's identity, the domain name, to a cryptographic key. Your device checks the signature on the certificate using the certificate authority's known public key. If the signature is valid, it means the certificate authority vouches for this server's identity. If the certificate has expired, or if it was signed by an authority your device doesn't trust, or if the domain name on the certificate doesn't match the domain you requested, the browser will warn you and may refuse to proceed. Assuming the certificate checks out, the two sides use a mathematical protocol to agree on a shared secret key. The elegant thing about this step is that they achieve it without ever sending the key itself over the network. They exchange enough information for both sides to compute the same key independently, using a technique called a key exchange. Anyone eavesdropping on the exchange can see the information being traded, but can't derive the key from it. This is one of the most beautiful results in modern cryptography, the idea that two parties can establish a shared secret in full view of anyone watching. Once both sides have the shared key, everything that follows is encrypted. Each chunk of data, each TLS record, is individually encrypted, authenticated, and integrity protected. If even a single bit is altered in transit, the receiver will detect the tampering and reject the record. The certificate the server presents is rarely self-standing. It is usually part of a chain. The server's own certificate is signed by an intermediate certificate authority, whose certificate is in turn signed by a root certificate authority, one whose public key is already embedded in your operating system or browser. Your device walks this chain from the server's certificate upward, verifying each signature along the way until it reaches a root it already trusts. If any link in the chain is broken, expired, or issued by an authority your device does not recognize, the verification fails, and the browser will not proceed quietly. The chain structure allows root authorities to delegate the daily work of issuing certificates to intermediaries without exposing their own keys, and it allows your device to trust a server it has never contacted before, provided the chain leads back to a foundation it recognizes. Once the encrypted channel is established, the data flowing through it is organized into records. Each TLS record is a bounded chunk of data, individually encrypted and individually authenticated. The record boundaries do not necessarily align with the boundaries of the HTTP messages traveling inside them. A single HTTP response might span many records, and a single record might carry fragments of more than one message. The encryption operates at the record level, sealing each chunk so that it arrives intact or is rejected entirely. This means that even within a long conversation between your browser and a server, no single record's compromise reveals the contents of the others. It's worth pausing here to note what TLS does and does not protect. TLS protects the content of the communication between your device and the server. The actual HTTP request, the page content, the cookies, all of it is encrypted and unreadable to anyone intercepting the traffic. But TLS doesn't make the connection invisible. An observer on the network can still see that your device is communicating with a particular server. They can see the volume of data flowing. They can see the timing of the exchanges. The contents are protected, but the fact that a conversation is happening and roughly how much is being said remains observable to varying degrees, depending on the network's architecture. Now let's take a breath and appreciate what has happened so far, because we're still in the first second or so after your click. Your device translated a name into an address using a distributed global database. It constructed packets and handed them to a chain of routers that independently forwarded them across a network of networks, using routing tables built through a protocol that lets tens of thousands of autonomous systems negotiate connectivity in real time. It established either a TCP connection or a QUIC connection to provide reliable, ordered data delivery. And it completed a cryptographic handshake to set up an encrypted channel that protects everything that follows. All of that happened before your browser sent a single byte of its actual request for the page you wanted. Let's send the request. The protocol your browser uses to ask for a web page is HTTP, The Hypertext Transfer Protocol, HTTP, defines the language of requests and responses that browsers and servers use to communicate. An HTTP request is straightforward. Your browser sends a message that includes the method, usually GET, which means, please give me this resource. It includes the path of the resource on the server, something like /articles, /how DNS -works. It includes headers, which are key value pairs providing additional information. The host header tells the server which domain you're requesting, which matters because a single server might host many different websites. Other headers convey what content types the browser can accept, what languages the user prefers, whether the browser has a cached version of the resource and when it was last retrieved, and various other details. The server receives this request, processes it, and sends back a response. The response includes a status code, a 3-digit number that tells the browser what happened. 200 means everything is fine. Here's the content you asked for. 301 means the resource has permanently moved to a different address. Go look there instead. 404 means nothing exists at that path. 500 means something went wrong on the server's end. Along with the status code, the response includes headers of its own, telling the browser what type of content is being sent, how long it is, how long it can be cached, when it was last modified, and other metadata. And then comes the body of the response, the actual content, the HTML document or image or style sheet, or whatever was requested. HTTP is what people call a stateless protocol. Each request-response pair is independent. The server doesn't inherently remember anything about previous requests from the same browser. If you load a page and then click a link on that page, the second request is a completely separate transaction from the server's perspective. Any sense of continuity, staying logged into an account, remembering items in a shopping cart, keeping track of preferences, is built on top of HTTP using mechanisms like cookies, not by the protocol itself. The vocabulary of HTTP is simpler than it might seem, and the terms shape every exchange your browser has with a server, so let's look at them a little more closely. The method is the verb that describes what the browser wants. Get means retrieve a representation of the resource. Post means submit data for the server to process, perhaps a form you filled out or a comment you wrote. There are others, but most ordinary browsing consists almost entirely of GET requests, quietly asking the server to send back whatever lives at a given path. The headers that travel alongside each request and response are pairs of names and values that carry context without being part of the content itself. Some tell the server what kinds of content the browser can accept. Some carry language preferences. Some tell the browser how long it may cache the response. They are the quiet metadata that shapes how both sides interpret the exchange, and most of them pass by without the person using the browser ever being aware of them. One small but important clarification is that what the server returns is a representation of the resource, not the resource itself. A resource is an abstract thing identified by the URL. The representation is the particular form the server chooses to deliver at this moment. Perhaps an HTML document, perhaps a block of structured data formatted for another program to read. The same resource might produce different representations depending on what the browser asked for. Redirects are another common part of the exchange. Sometimes the server responds not with the content you requested, but with a new address, where that content now lives, or where the server would prefer you to look. The browser follows the redirect automatically, sending a fresh request to the new location, and you rarely notice that it happened. A site that has reorganized its pages, or a short link that expands to a longer address, relies on this mechanism. And then there are cookies, those small parcels of state that bridge the gap between a stateless protocol and the continuity you experience as a user. When a server wants to remember something about your session, it sends a cookie to your browser along with a response. Your browser stores it and sends it back with every subsequent request to the same server. This is how a server recognizes that two separate requests came from the same visitor. The protocol itself carries no memory, but the browser carries the cookie forward, one small label at a time, like a return address note the server wrote and the browser dutifully holds on to. And here's a distinction that people blur all the time, but it matters. The internet and the web are not the same thing. The internet is the global network of networks. It's the physical and logical infrastructure that carries packets from one place to another using IP and BGP and all the routing machinery we've been discussing. The internet existed before the web. Email ran on the internet. File transfer ran on the internet. Remote login ran on the internet. These applications used the internet's packet delivery to communicate, and they still do. The web is one specific application that runs on the internet. It's the system of linked documents, transferred using HTTP, written in HTML, addressed with URLs, that you navigate with a browser. The web was invented by a specific person at a specific time, and it's a layer on top of the internet, not the internet itself. The person was Tim Berners-Lee, a British computer scientist working at CERN, the European Particle Physics Laboratory near Geneva. In 1989, Berners-Lee wrote a proposal for a system to help researchers at CERN share information more easily. The lab had thousands of scientists from dozens of countries, each using different computers, different operating systems, different document formats. Finding information and sharing it across the organization was frustratingly difficult. Berners-Lee proposed a system built on three inventions. First, a way to address any piece of information on any computer, anywhere on the network, using a uniform resource identifier, what we now call a URL. Second, a protocol for requesting and delivering documents, HTTP. Third, a language for writing documents with embedded links to other documents, HTML, the hypertext markup language. Together, these three things created the web, a space where any document could link to any other document, forming an interconnected web of information with no central index and no single authority controlling what could be published. By the end of 1990, Berners-Lee had built the first web browser and the first web server, running on a Next computer at CERN. He used them to serve a simple page that explained what the web was and how to use it. That page, served from a single computer in a physics laboratory in Switzerland, was the entire World Wide Web. In 1993, CERN made a decision that would shape the next 3 decades of technology and culture. They released the web software into the public domain, making it freely available for anyone to use, modify, and build upon. No license fees, no restrictions, no permission needed. That decision shaped the next 3 decades of technology and culture. It meant that anyone could build a web server, anyone could write a web browser, anyone could create web pages and link them to anything else. The web grew explosively because nobody needed to ask permission to participate. Within a few years, it had become the dominant way people used the internet, and it has remained so ever since. But the web is not the internet. If the web disappeared tomorrow, the internet would keep running. Email would work, video calls would work, file transfers would work. All the other applications that use the internet's packet delivery infrastructure would keep going. They're different applications running on the same network, just like email and web browsing are different apps running on the same phone. Now let's come back to your HTTP request, because the server has received it and is preparing the response. And this is where the journey takes a turn that might surprise you, because the server that answers your request might not be a single machine sitting in a single location. For small websites, the request might go to a single server in a data center somewhere, a machine running web server software that finds the right file and sends it back. But for many websites, especially popular ones, the response comes from a content delivery network, usually called a CDN. A CDN is a system of servers distributed around the world, each one holding copies of the same content. When your request arrives, the CDN routes it to whichever server is closest to you, either geographically or in terms of network distance. The idea is straightforward. If you're in Sydney and the website's origin server is in Amsterdam, sending your request all the way to Amsterdam and waiting for the response to travel all the way back adds latency. But if the CDN has a copy of that page on a server in Sydney, your request only has to travel within the city. The response comes back much faster. CDNs also distribute load. When a website gets millions of simultaneous requests, the CDN spreads that traffic across hundreds or thousands of servers instead of concentrating it all at one origin. This is how websites survive sudden surges in traffic, a news event, a product launch, a viral link, without falling over. And CDNs interact with HTTP's caching system in an important way. HTTP has built-in rules for caching. When a server sends a response, it can include cache control headers that specify whether and for how long the response can be stored and reused by intermediate systems. These headers tell your browser's cache, the CDN's cache, and any other caches along the path whether they're allowed to serve a saved copy instead of forwarding the request all the way to the origin server. If the content hasn't changed since the cached copy was stored, there's no reason to fetch it again. The cache can revalidate with the origin, essentially asking, has this changed since I last fetched it? And if the answer is no, it serves the cached copy. This saves time, reduces bandwidth, and takes load off the origin server. So the response your browser receives might have originated from a server on the other side of the planet, or from a CDN node a few miles away, or from your own browser's local cache if you visited the same page recently. The path depends on the caching rules, the CDN configuration, and how recently someone nearby asked for the same thing. Picture the possible stops your request might make on its way to an answer, because the path is not always the same, and no single diagram describes every site on the web. In a common arrangement, the first thing your request encounters after crossing the network is an edge server, a machine positioned close to you whose primary job is to check whether it already has a valid cached copy of what you asked for. If it does, the journey ends right there, answered from a shelf within reach. If it does not, the request moves inward toward the origin. Behind the edge, there is often a load balancer, a device whose job is to decide which of several application servers should handle this particular request. When a site runs on many machines, the load balancer distributes incoming requests among them so that no single server is overwhelmed. It makes this decision quickly and forwards your request onward. The application server that receives the request is where the actual work of composing a response begins. It reads the path and the headers, determines what is being asked for, and reaches into whatever storage holds the answer. That storage might be a database, a file system, a distributed object store, or several of these working together. For a simple static page, the work might be nothing more than reading a file and sending it back. For something more dynamic, the server might query a database, apply logic that decides what to include, assemble content from several sources, and build the response piece by piece before handing it to the network for the return journey. Not every site uses all of these layers. A small personal blog might be a single server with no load balancer and no separate edge cache. A large service might have many layers between you and the machine that finally composes your answer. The architecture is shaped by scale and by the nature of what is being served, and there is no universal blueprint. What is consistent is the principle. Each layer either answers the request from what it already knows or passes it deeper until something can. Now let's talk about the response itself, because what comes back to your browser isn't a finished page. It's a set of instructions for building one. The server sends back a document written in HTML. HTML describes the structure of the page as a hierarchy of elements. Headings, paragraphs, links, images, lists, forms, tables, sections, all described as nested elements with attributes that provide additional information, like the address of an image or the destination of a link. Your browser reads this HTML from beginning to end and starts constructing the page. But the HTML document is rarely the only thing the page needs. It typically references other resources, style sheets written in CSS that control how the page looks, specifying colors, fonts, sizes, spacing, layout. Scripts written in JavaScript that control how the page behaves, responding to clicks, updating content dynamically, validating form inputs, images, fonts, videos, icons, each one a separate file at its own address. Each of these referenced resources requires a separate HTTP request. When the browser encounters a stylesheet reference, it sends a request for that file. When it encounters an image, another request. A complex modern web page might reference 50 or 100 separate resources, each one fetched through its own request-response cycle. The browser does this in parallel wherever it can, opening multiple connections and fetching several resources simultaneously. Modern versions of HTTP, specifically version 2 and version 3, are designed to make this multiplexing efficient. HTTP version 2 allows many requests and responses to flow simultaneously over a single TCP connection, interleaved in a way that avoids the head-of-line blocking problem at the HTTP level, though TCP's head-of-line blocking still applies at the transport level. HTTP version 3, which runs on QUIC, eliminates even that transport-level blocking by using QUIC's independent streams. Each of those additional requests goes through the same chain we've been tracing. DNS lookup, if the resource is hosted on a different domain. Connection establishment, if there isn't already one open to that server. TLS handshake, if it's a new secure connection. HTTP request, response. The page you see in your browser is the assembled result of potentially dozens or hundreds of separate request and response cycles, each one traveling through the same layers of protocol and infrastructure. As the resources arrive, your browser builds the page in stages. It parses the HTML into a tree structure called the document object model that represents the document's content and hierarchy. It processes the CSS and combines it with the DOM to build a render tree that maps every visible element to its visual properties, size, position, color, font. It executes JavaScript that might modify the DOM or the styles, adding or removing elements, changing appearances, setting up event handlers that will respond to your clicks and keystrokes and scrolls. Then comes the actual painting. The browser calculates where every element goes on the screen, a process called layout. It determines the stacking order, which elements appear in front of which others. It rasterizes text, selecting the right glyphs from the font files. It decodes images from their compressed formats into pixel data, and it composites everything into the final visual frame, the image that appears on your display. This rendering process is itself a remarkably complex piece of engineering. Modern browsers have rendering engines that rival operating systems in their complexity, with hardware-accelerated compositing, sub-pixel text rendering, advanced color management, and optimization techniques that took decades to develop. But that's a story about browsers rather than about networks, so we'll set it aside for another night. Let's turn to the physical journey now, because we've been talking about protocols and software, and there's a dimension of this story that lives in the physical world. The cables, the fibers, the machines in buildings you'll never visit, the infrastructure that sits beneath every abstraction we've discussed. When your data leaves your device, it travels first through whatever connection you have to your local network. If you're on Wi-Fi, it goes as radio waves to a small router, a box about the size of a book, that converts between the radio signals your device sends and the electrical or optical signals that travel through the wired network. From your router, the data travels over a wire, usually fiber-optic cable, but sometimes copper, to equipment operated by your internet service provider. This first link might run along the outside of your building, down a street, through a conduit under the sidewalk, or along utility poles, eventually reaching a neighborhood aggregation point where your connection joins the connections of your neighbors, and from there to a larger facility that connects to the provider's backbone network. The provider's backbone is a network of high-capacity links connecting major cities and regions. These links are typically fiber-optic cables carrying data as pulses of light through thin glass strands. A single fiber can carry enormous amounts of data using a technique called wavelength division multiplexing, which sends multiple signals at different colors of light through the same fiber simultaneously, each color carrying its own independent data stream. Your data travels through this backbone, passing through routing equipment at various points, until it reaches a location where your provider connects to other networks. These connection points are called Internet Exchange Points, or IXPs, and they're the physical places where different networks meet and exchange traffic. Some Internet Exchange Points are in nondescript buildings in industrial areas. Some are in purpose-built data center campuses. From the outside, they're unremarkable. Inside, they're rooms full of equipment, racks of routers and switches, each one belonging to a different network, connected to a shared switching fabric through bundles of fiber-optic cables. The exchange fabric is like a shared table where everyone can talk to everyone else. Your internet provider's router sits in one rack. A large content company's router sits in another rack. A hosting provider's router sits in a third. They're all connected to the same exchange fabric, and they can all exchange traffic directly without needing to send data through anyone else's network. The alternative to exchanging traffic at an IXP is to use a transit provider, a network that you pay to carry your traffic to parts of the internet you can't reach directly. Transit is essentially paying someone else to carry your packets because you don't have a direct connection to the destination. Peering, the direct exchange at an IXP, is usually cheaper and faster. The negotiations around who peers with whom and on what terms are one of the hidden economic dynamics of the internet, relationships that shape the paths your data takes, even though you never see them. Whether your data actually crosses a national border or an ocean, at this point, depends entirely on where the content lives. Many popular services distribute copies of their material across data centers in dozens of cities and countries, and content delivery networks cache pages and media at edge locations close to the populations that request them most often. If the page you asked for is hosted by a service with infrastructure near you, the exchange might stay within your own city or region. The data travels through your provider's network, reaches an exchange point or a direct interconnection with the hosting network, and the answer comes back without crossing any border at all. A surprising share of everyday web traffic resolves this way, answered by a server that is geographically close, either because the origin happens to be nearby or because a cached copy was placed there deliberately. The points where your data passes from one network to another are where the structure of the internet becomes most tangible. At an internet exchange point, dozens or sometimes hundreds of separate networks connect to a shared switching fabric housed in a single facility. Each network brings its own routers, its own fiber, and its own traffic, and the exchange provides a neutral meeting place where any two of them can agree to pass data directly between their equipment. This direct exchange is called peering, but not every destination can be reached through peering at the nearest exchange. When a network cannot reach a particular address through any of its peering partners, it hands the traffic to a transit provider, a larger network that has agreed, for a fee, to carry the data onward and deliver it through its own broader set of connections. Your data might pass through several of these handoffs on a single journey, peering at one exchange, transit through a paid carrier, peering again at another exchange further along, before it reaches the network where the server lives. When the content does live farther away, the path your data takes is shaped not by geography alone, but by the policies and commercial agreements that govern traffic between autonomous systems. The Border Gateway Protocol does not choose routes the way a person might choose a driving route, favoring the shortest distance on a map. It selects paths based on who has agreed to carry whose traffic and under what terms. A network might prefer to send your data through a more distant exchange point because it has a settlement-free peering arrangement there rather than paying a transit provider for a physically shorter path. The result is that your data's route can look surprising when traced on a globe. It might cross a continent to reach a server in a neighboring country, not because there is no closer path, but because the closer path costs more or simply does not exist as a negotiated relationship between the networks involved. As your data moves through these terrestrial links, It travels as light. In the fiber-optic cables that form the backbone of most modern networks, information is encoded as rapid pulses of laser light passing through a strand of glass thinner than a human hair. The light moves through the fiber by total internal reflection, bouncing along the inside of the glass core in a guided path, traveling at roughly 2/3 the speed of light in a vacuum. Over distance, the signal gradually weakens. Glass is remarkably transparent, far more so than ordinary window glass, but not perfectly so, and after some tens of kilometers, the signal has faded enough to need help. On land, optical amplifiers positioned along the route boost the weakened signal without converting it from light back into electricity. The light stays as light, which is part of what gives modern fiber networks their speed. And through wavelength division multiplexing, many independent signals at different wavelengths of light travel through the same fiber simultaneously, each one carrying its own data stream, sharing the glass without interfering with one another. If your data needs to cross an ocean, it arrives at a cable landing station. These are typically unassuming structures built on or near a coastline, sometimes in ordinary industrial areas of port cities or quiet coastal towns. Inside, the terrestrial fiber network meets the submarine cable system. The landing station is the transition point where the optical signal passes from the land-based infrastructure into the cable that will carry it beneath the sea. The station also houses power-feeding equipment that supplies a steady electrical current to the cable, because the components on the ocean floor need energy, and there is no way to deliver it except through a conductor running inside the cable itself from the shore. Each end of a submarine cable has its own landing station, and between those two buildings, the cable stretches across the continental shelf and the deep ocean floor. If the server you're requesting data from is nearby, on the same continent or in the same region, your data might stay on land the entire time. It might travel through a few hundred kilometers of fiber-optic cable, pass through one or two exchange points, and arrive at a data center where the server lives. The round trip might take 10 or 20 milliseconds. But if the server is on another continent, your data almost certainly travels under the ocean. And that fact sounds surprising until you think about it, and then it becomes genuinely fascinating. Nearly all of the data that moves between continents travels through submarine fiber-optic cables. These are cables that lie on the ocean floor, connecting landing stations on one continent to landing stations on another, across thousands of kilometers of open sea. A report published by the International Telecommunication Union in 2026 examined the resilience of submarine cable networks and described these cables as carrying more than 99% of intercontinental data traffic. Satellites carry some traffic, particularly to remote areas and ships at sea, but the volume of data moving between major population centers on different continents flows overwhelmingly through submarine cables. A modern submarine cable system consists of several components. At each end, there's a landing station, a building on the coast where the cable comes ashore. The cable runs from the landing station out to sea, crossing the continental shelf, descending to the deep ocean floor, crossing the ocean basin, ascending the continental shelf on the other side, and arriving at another landing station. The cable itself is not very large. In the deep ocean, where the cable sits on the seabed far from human activity, it can be surprisingly thin. Closer to shore, where it's at risk from fishing nets, anchors, and construction, it's armored with layers of steel wire and is considerably thicker. In shallow water, the cable is often buried in a trench below the seabed for additional protection. Inside the cable, the actual data-carrying element is fiber-optic strand, thinner than a human hair. Light pulses travel through this fiber, encoded with data using modulation techniques that pack enormous amounts of information into the variations of the light signal. A single modern fiber pair can carry many terabits of data per second, and a cable typically contains multiple fiber pairs, giving it aggregate capacity that's almost difficult to comprehend. Spaced along the cable at regular intervals are repeaters. A repeater is a sealed unit that amplifies the optical signal as it weakens during its journey through the fiber. Light loses strength as it travels through glass, and without amplification, the signal would become too faint to read after a relatively short distance. The repeaters boost the signal back to usable levels, allowing it to cross entire ocean basins. The repeaters are powered by electrical current carried through a copper conductor that runs alongside the fiber inside the cable. The power is fed into the cable from the landing stations at each end, and the voltage can be substantial, enough to push current through thousands of kilometers of conductor and keep every repeater along the way operational. A single transatlantic cable might need to power many repeaters, each one sitting on the ocean floor in total darkness, under enormous pressure, with no possibility of routine maintenance. They're designed to operate for the full planned life of the cable system. Not all submarine cable systems use repeaters. The ITU's guidance on submarine system design distinguishes several approaches based on how the optical signal is maintained over distance. Repeated systems are used for long ocean crossings, with amplifiers housed in sealed units spaced along the cable to keep the signal strong across thousands of kilometers. But shorter crossings over a narrow sea or a strait between nearby landmasses sometimes use a simpler design. A repeaterless system carries no active components on the seabed at all. The cable runs from one landing station to the other, relying entirely on the strength of the initial signal and the quality of the fiber to deliver a readable pulse at the far end. The achievable span is limited, but for shorter routes the advantage is significant. Nothing on the seabed requires power, nothing can fail as a powered component, and the cable is simpler to build and deploy. Between these approaches sit optically amplified systems of various configurations, some using techniques where amplifying energy is delivered from the landing stations through the fiber itself, rather than through a separate electrical conductor. Some cable systems also include branching units, sealed housings placed at points along the route where the cable divides. A branching unit allows a single trunk cable to split into two or more branches, each heading toward a different landing station in a different country. This is how one cable system can serve several nations along its path without requiring a separate cable for each pair of endpoints. The branching unit is among the more complex components on the seabed because it must reliably direct optical signals and distribute electrical power across multiple branches while operating under enormous water pressure with no prospect of routine servicing. Each branch may terminate at a landing station hundreds of kilometers from the branching point, and the entire assembly is designed to function without human intervention for the operational life of the system. The submarine cable industry builds deliberate geographic diversity into its network. When a new system is planned, its route is often chosen to follow a different path from cables already in service between the same regions. If two cables connecting the same pair of continents cross the ocean at different latitudes or make landfall at different coastal cities, a single event along one route is far less likely to affect the other. This geographic separation is one of the primary defenses against large-scale disruption. It is reinforced by the sheer number of cables now in service. Dozens of submarine systems connect Europe and North America. Dozens more link Asia to the Americas and to Europe and to Africa. The loss of any single cable is a manageable event because the traffic it carried can redistribute across the surviving systems through the same routing adjustments that handle failures on land. When something does go wrong, the fault is usually detected before most users notice anything has changed. Monitoring equipment at the landing stations continuously measures the characteristics of the optical signal passing through the cable. A break or a sharp degradation produces an immediate and distinctive change in those measurements that the monitoring system registers within moments. In many cases, the equipment can estimate how far along the cable the fault has occurred by analyzing the pattern of signal change, giving the repair teams a starting point for locating the damage on the ocean floor. Meanwhile, the routing infrastructure has already begun shifting traffic onto alternative cables, and for well-connected routes, the switchover happens quickly enough that users experience at most a brief rise in latency rather than a visible loss of service. When a submarine cable breaks, and they do break, the most common cause is human activity. Fishing trawlers dragging nets or anchors across the seabed, account for the majority of cable faults in shallower waters. Earthquakes and underwater landslides can damage cables in seismically active areas. Natural abrasion from currents and sediment movement can weaken cables over time. When a break occurs, traffic is rerouted to other cables, if they exist along that route. This rerouting happens automatically through the BGP system we discussed earlier. The routers at the landing stations detect the loss of the cable and update their routing advertisements, and within seconds or minutes, traffic is flowing along alternative paths. The Internet's routing system was designed for exactly this kind of failure. Meanwhile, a specialized cable repair ship is dispatched to the break location. These ships carry spare cable, splicing equipment, and remotely operated vehicles that can work at great depths. The ship locates the break, grapples the cable from the ocean floor, brings the broken ends to the surface, cuts out the damaged section, splices in new cable, and lowers it back down. In deep water, the grappling process alone can take days. The entire repair can take weeks, depending on the weather, the depth, and how remote the location is. The submarine cable network is one of those hidden systems that the modern world depends on without most people knowing it exists. International financial transactions, diplomatic communications, scientific collaboration, video calls between family members on different continents, streaming entertainment, cloud computing, virtually everything that crosses an ocean travels through these thin glass fibers lying quietly on the seabed. And the idea of sending signals through cables across the ocean floor is far older than the Internet. The first transatlantic telegraph cables were laid in the middle of the 19th century, connecting Ireland to Newfoundland. Early attempts lasted only weeks before the insulation failed and the signal degraded to nothing, and it took several more attempts before a reliable cable was finally completed. Within a few decades, submarine telegraph cables connected most of the world's major commercial centers. The technology has changed completely since then, from copper carrying electrical pulses to glass carrying light, from telegraphy to terabits. But the basic engineering challenge, running a communication line along the seabed from one continent to another and keeping it working for years in a place that wants to crush and corrode everything humans build, has been with us for more than 150 years. What connects those early telegraph engineers to the people who design and maintain submarine fiber systems today is the continuity of the work itself. Cable ships have been sailing to lay and repair ocean cables for more than a century and a half. The skills involved, route surveying, cable handling, deep water operations, fault location, have evolved alongside the technology, but never vanished. The ships themselves have changed from steam-powered vessels with mechanical drums to modern dynamically positioned ships guided by satellite navigation, but the essential task, lowering a manufactured line to the ocean floor and confirming it works when it arrives, remains recognizable across the generations. The community of people who build and tend submarine cables is small and specialized, and their knowledge passes forward in an unbroken line that runs from the earliest telegraph ventures through coaxial telephone cables to the fiber-optic systems carrying nearly all intercontinental data today. As we follow this imaginary click, it helps to remember that the ocean crossing is not guaranteed. Your request travels beneath the sea only if the server holding what you asked for sits on the far side of an ocean from where you are. If the service hosts its content in your own country, or if a content delivery network has placed a cached copy at a location near you, the submarine cables play no part in your particular journey tonight. They are carrying an enormous volume of other traffic at this moment, but not necessarily yours. The path your data takes is shaped by where you are and where the answer lives, and the network is indifferent to whether any particular click crosses an ocean or never leaves a single city. It follows the addresses and the routing tables, one hop at a time, wherever they lead. Let's come back to your request now, because while we've been talking about the physical infrastructure, the server has been preparing its response. The response travels back through the same layers in reverse, from the server, through the data center's internal network, out to the data center's uplink, through the routing infrastructure, possibly under an ocean, possibly across a continent, through exchange points and transit links, back to your internet provider's network, through the local infrastructure to your router, and over Wi-Fi or wire to your device. The response packets might not all take the same physical path. One packet might route through one set of routers, while another routes slightly differently. This is perfectly normal. IP doesn't require packets belonging to the same connection to follow identical paths. Each router makes its own forwarding decision for each packet independently. The transport layer, TCP or QUIC, handles the reassembly. It puts the packets back in order, detects any that went missing, requests retransmissions, and delivers a clean, ordered data stream to the browser, regardless of the messiness underneath. And here's something to think about as you picture this happening. Your QUIC didn't launch one request. It launched potentially dozens. The initial HTML document triggered additional requests for style sheets, scripts, images, fonts, and other resources. Each of those might be served from a different domain, hosted on a different CDN, physically located on a different continent. Your browser might be simultaneously communicating with 5 or 10 or 15 different servers, each connection managed independently, each going through its own DNS lookup, connection handshake, and encrypted channel. The browser coordinates all of these into a single coherent page that appears on your screen as though it were one simple thing that was always there. The path the response takes back to your device does not have to mirror the path the request followed outward. Each packet in the response is a separate traveler, and the routers it meets along the way consult their own forwarding tables at the moment the packet arrives. If a link has become congested since the request passed through, or if a routing update has shifted the preferred path, the response packets may cross different routers, different exchange points, even different submarine cables than the ones the request used minutes earlier. The two directions of the journey are independent. The network treats each packet on its own terms, and neither direction remembers or constrains the other. When a response packet arrives at your device, the transport layer has work to do before the browser sees anything useful. Each packet carries a small mathematical summary of its own contents, computed by the sender before the packet left. Your device runs the same calculation on the data it received and compares the two results. If they match, the data almost certainly survived the journey without corruption. If they do not match, the data was damaged somewhere along the way, and the transport layer discards the packet quietly rather than handing broken information upward. This check is simple and fast, but it catches the kind of silent errors that cables, routers, and radio links occasionally introduce. A flipped bit, a garbled byte, the kind of damage that would be invisible without a deliberate integrity check. Beyond detecting corruption, the transport layer must also handle absence. Not every packet that leaves the server will arrive. Some are dropped by congested routers. Some are lost to brief interruptions on a wireless link. The transport protocol notices these gaps because the sequence of arriving packets has holes in it. With TCP, the receiver signals the sender by acknowledging only as far as the last contiguous byte it holds, and the sender interprets the stalled acknowledgement as evidence that something went missing. It sends the missing data again. With QUIC, the same principle applies within each individual stream. So a lost packet on one stream does not hold up data on a different stream traveling inside the same connection. In both cases, the transport layer waits, fills the gaps, and delivers the bytes in the correct order. The browser above never sees the chaos. It receives a smooth, unbroken flow of data, as if the network had been perfectly reliable all along. Before the browser can read any of that data, one more layer of work must happen. The bytes arriving from the transport layer are still encrypted. Each chunk is sealed inside a TLS record, and your device must open each record before the content inside becomes visible. Opening a record means using the session key that your device and the server agreed on during the handshake to reverse the encryption and verify that the record was not altered in transit. TLS checks each record individually. If even one byte was changed between the server and your device, the integrity check fails and the record is rejected. Only after a record passes both decryption and integrity verification does the plain text inside become available to the layer above. This is the moment when the HTTP response the actual content of the server's reply finally becomes readable on your device. What the browser finds inside that response begins with a set of headers. These are short lines of text that describe the content without being the content itself. One header names the type of material the server is sending, whether it is an HTML document, an image, a style sheet, or something else. Another header may describe the encoding used to compress the content for transfer, so the browser knows how to decompress it before reading. Others specify caching rules, telling the browser whether it may store this response and for how long, or they carry a timestamp showing when the content was last changed. The headers are the label on the package. They tell the browser what is inside and how to handle it. After the headers comes the body, the actual content, which for a web page is typically a document written in HTML. The browser does not wait for the entire document to arrive before it begins working. As soon as the first bytes of HTML start flowing in, the browser begins reading them. It moves through the markup the way you might read a long letter, line by line, building understanding as it goes. Each element it encounters, a heading, a paragraph, a link, an image reference, is added to a growing structure in memory called the document tree. Think of it as a family tree for the page, where each element knows its parent, its children, and its neighbors. The tree grows incrementally as more of the document arrives. The browser does not need the whole letter in hand before it starts understanding what it says. While the document tree is being built, the browser also encounters references to style sheets, separate files written in a language called CSS that describe how the page should look. When the browser fetches and reads a style sheet, it builds a second structure, a set of rules that map visual properties to the elements in the document tree. This element should be a certain color. That heading should use a particular font. This paragraph should have a certain amount of space around it. The browser then walks through the document tree and calculates, for every visible element, the full set of visual properties that apply to it. This step is called style calculation, and it produces a clear answer for every element. What color, what size, what font, what spacing, what borders, what background. With the style settled, the browser can figure out where everything goes. This step is called layout, and it is the moment when abstract descriptions become physical positions. The browser measures text, accounts for the width of the screen, respects the spacing rules from the style sheet, and assigns every visible element a position and a size, the way a typesetter arranges lines of text on a page, working from the top down, fitting each piece into the space that remains. If you imagine the screen as a blank sheet of paper and each element as a card with specific dimensions, layout is the process of placing every card in its correct position, one after another, following rules about how they relate to each other. After layout, the browser paints. Painting is the step where positions and styles become actual pixels. The browser draws the background colors, renders the text using the correct glyphs from the font files, decodes images from their compressed formats, draws borders and shadows, and fills in every visible surface. Then it composites, layering all of these painted pieces together in the correct stacking order, handling transparency and overlap, and producing the final image that appears on your display. The whole sequence, tree construction, style calculation, layout, paint, compositing, happens so quickly that the page seems to appear all at once. But underneath, each step builds on the one before it, and every step must finish before the final picture is complete. As the browser reads through the HTML, it discovers that the page depends on more than just the document itself. The markup contains references to images, fonts, style sheets, and scripts, each one living at its own address. Every one of these sub-resources needs its own small network journey. The browser sends a fresh request for each one, and each request passes through the same chain we traced for the original page. DNS lookup if the resource lives on an unfamiliar domain. Connection and handshake if no open connection exists to that server. HTTP request and response. TLS decryption. The page you eventually see is not one document, but many, assembled from pieces that may have arrived from different servers in different cities. For many of these sub-resources, the browser checks its cache first. the same local store it consulted for the original page. If a style sheet was fetched an hour ago and the server said it could be reused for a full day, the browser serves it from memory without touching the network. If the cached copy has aged past its freshness window, the browser can still avoid a full download by asking the server a lighter question. Has this file changed since the copy I already have? The browser sends a conditional request, including a timestamp or an identifier from the cached version, and the server either confirms that the old copy is still valid or sends the new one. On a page with dozens of sub-resources, this quiet reuse saves enormous amounts of time and bandwidth. Many of the pieces arrive instantly from local storage, and the ones that need checking often come back as a brief confirmation rather than a full transfer. There is one more boundary the browser enforces as all of these pieces arrive, and it is one you never see but always benefit from. The browser maintains strict rules about which parts of a page are allowed to interact with which other parts, based on where they came from. A script loaded from one origin cannot freely read data fetched from a different origin. An image served from one domain cannot be inspected pixel by code running on behalf of another domain, not without explicit permission from the server that provided it. These boundaries exist because a single web page often assembles content from many independent sources, and without rules, a malicious script on one site could silently read your private data from another. The browser treats each origin as its own small territory, and crossing between territories requires the consent of both sides. So let's gently retrace the thread of the whole journey, because if you have been drifting in and out, this is a good place to come back. You tapped a link. Your device read a small address from the page, translated that address into a number, using the distributed naming system we walked through earlier, and sent a request out across a chain of networks. The request traveled as a series of small packets, each one forwarded independently by routers that knew only the next step, not the full path. It passed through your provider's network, possibly through exchange points, where different networks meet, possibly through cables under the ocean, and arrived at a server that held what you asked for. The server composed a response and sent it back along whatever route the network chose at that moment. Your device's transport layer caught every arriving packet, checked it for damage, filled in any gaps, and delivered a clean stream of bytes. The encryption layer unsealed the data so the browser could read it. And the browser took that stream of instructions and built a living page out of it, piece by piece, fetching every image and font and style sheet it needed along the way, checking its own memory first, and painting the final result on your screen. All of it in roughly the time it takes to draw a breath. This layered architecture, where each protocol handles one concern without needing to understand the internals of the layers above or below it, is one of the most important design decisions in the history of the Internet. The people who built these systems didn't try to create a single protocol that did everything. They built separate protocols for addressing, routing, reliable delivery, encryption, and application-level communication, and they stacked them on top of each other. Each layer trusts the layer below it to do its job, and each layer can be improved or replaced independently without breaking anything else. This is why the Internet has been able to evolve so dramatically over decades without being rebuilt from scratch. TCP has been improved many times since the 1970s, with better congestion control, faster loss recovery, and support for higher speeds. IP has been upgraded from version 4, with its limited address space of about 4 billion addresses, to version 6, which supports a number of addresses so large that every grain of sand on Earth could have its own, and there would still be addresses left over. TLS has progressed through multiple versions, each one closing security vulnerabilities and streamlining the handshake. HTTP has evolved from version 1 to 1.1 to 2 to 3, each with significant changes to how data is transferred. And QUIC has been introduced as an entirely new transport option. None of these changes required tearing up and replacing everything else. Each one was swapped in at its layer, while the other layers kept running. Let's slow down now and sit with the full picture, because we've traveled a long way from that click, and it's worth seeing all the layers together before we're done. At the bottom, there's physics. Light traveling through glass fibers at roughly 2/3 the speed of light in vacuum. Electrical signals on copper wire. Radio waves between your device and your router. These are the raw materials, photons and electrons and electromagnetic waves, carrying patterns that represent information. On top of the physics, there are protocols for addressing and routing. IP gives every device a number and provides a way to carry packets from one number to another. BGP lets the autonomous systems that make up the internet share routing information, so packets can find their way through a mesh of independently operated networks. Together, they create a global delivery system that can move a packet from any connected device to any other connected device, even if the two have never communicated before and are on opposite sides of the planet. On top of routing, there are protocols for reliable communication. TCP or QUIC take the unreliable, best-effort packet delivery that IP provides and build a dependable, ordered data stream on top of it. They detect lost packets and arrange retransmissions. They manage the speed of data flow so senders don't overwhelm receivers or the network. They give applications the abstraction of a simple, direct pipe between two machines, hiding all the chaos of the real network behind a clean interface. On top of reliable communication, there's encryption. TLS wraps the data in cryptographic protection, verifying identities through certificates, establishing shared keys through mathematical protocols, and encrypting every record of data so it can't be read or modified by anyone between the endpoints. And on top of all of that, there's the application layer, HTTP, the protocol your browser uses to request and receive documents. HTML, the language those documents are written in. URLs, the addressing system that identifies specific resources on specific servers. CSS for visual presentation. JavaScript for dynamic behavior. The whole web, the thing you interact with every day without thinking about it, is built on this stack of layers. And underneath all the software, there's physical infrastructure. Cables under streets and oceans. Routers in windowless buildings with backup generators and redundant cooling. Servers in data centers drawing significant electrical power. Internet exchange points where dozens of networks plug into shared switching fabrics. Repeaters on the ocean floor, amplifying light pulses in total darkness under enormous water pressure, year after year. Every one of these layers was designed by people solving a specific problem at a specific moment in history. Mockapetris designed DNS because a single text file couldn't keep up with a growing network. Davies and Barron and Kleinrock developed packet switching because circuit switching was wasteful and fragile. Cerf and Kahn designed TCP and IP because they needed a way to connect different kinds of networks into a single coherent system. The cryptography community developed TLS because people needed private communication on a public network. Berners-Lee designed the web because physicists at a laboratory needed a better way to share their papers. Each solution became a foundation for the next problem, and the whole system grew organically, one layer at a time, over decades. None of it was planned from the top down. Nobody sat in a room in 1969 and designed the system that exists today. Each generation of engineers inherited what the previous generation built, identified the next problem, and added their own layer. And the reason the whole thing works, the reason it has kept working and kept growing for more than 50 years, is that each layer was designed with clean boundaries. Each protocol does one thing, and does it well. Each layer trusts the layer below, and serves the layer above, and anyone can build something new on top, without asking permission. And tonight, these same systems are carrying whatever brought you this audio. The same DNS translated the address. The same TCP or QUIC is delivering the data reliably. The same TLS is protecting the stream. The same routing infrastructure is finding a path between the server and your device. The same submarine cables might be carrying the signal across an ocean. Every layer is active right now while you listen. The next time you click a link and a page appears, you'll know what happened underneath. Your device asked a distributed naming system for an address. It sent packets through a network of networks, each router making its own forwarding decision based on routing information shared through BGP. It established a transport connection for reliable delivery. It completed a cryptographic handshake to protect everything that followed. It sent an HTTP request. The server responded, possibly from a cache nearby, possibly from the other side of the world. The response traveled back through the same infrastructure. The transport layer reassembled the packets. TLS decrypted the data. The browser parsed the HTML, fetched the referenced resources, applied the styles, executed the scripts, and painted the final page on your screen. Dozens of resources fetched through their own chains of protocols, all happening in parallel, all invisible, all finished before you've noticed it started. The systems keep running. They carry data for billions of people simultaneously, around the clock, around the world, and they do it so reliably that we've stopped noticing. A page loads, a message arrives, a video plays, and it just works. The machinery is invisible, and that invisibility is perhaps the highest compliment anyone can pay to the people who designed it. They built something so reliable that the world forgot it was there. That's what happens after you click a link, and it's been happening, in some form, since 1969, when 4 nodes at 4 universities exchanged their first packets and proved that the idea could work. Everything since then has been refinement. Faster fibers, smarter routing, stronger encryption, better protocols. But the core idea, break the message into pieces, send them independently through a network of networks, and reassemble them at the other end, that idea has held for more than 50 years. It held because it was the right idea, and it held because the people who built on it kept the layers clean, kept the interfaces open, and kept the system free enough for anyone to build the next thing on top of it. Sleep well. The network will still be here in the morning.